Calculus! It's entirely possible that at one point or another in your life, you've heard of it before. A lot of people, at least the people that I'm familiar with, tend to treat it as something that's like notoriously difficult and only for geniuses, and honestly, that's understandable. I mean, granted, it's no rocket science, but it can be difficult if you don't know what you're doing. I mean, yes, really, you could say that about any branch of mathematics, come to think of it. But I feel like with calculus, I really need to emphasize that. Like, really, really need to emphasize it. Because here's the thing, and you've probably heard this from your math teacher already, but if you're missing something, it's gonna make going forward a lot more difficult. Anyways, I think that's enough of the intro monologue. What you're here for is the mathematics, the calculus part. I mean, you're basically watching a calculus tutorial on YouTube. Otherwise, I don't know why you'd be here right now. Anyways, this would end up being a lot of footage to actually work on at once, if I did everything, because this recording is just limits. I'm doing a voiceover right now, and this thing is like 30 minutes long, so I'm gonna split this into a 5-part series. Now, we'll start with, the first topic I would like to cover, because this is the first episode, and it's actually based on the first unit of AP Calculus, because, well, I mean, it's a pretty fundamental concept. Limits! And continuity. Now, for a bit of context, calculus is made up of 3 general concepts. Limits, differentiation, I almost wrote integration there, and then integration. Of course, with this being the limits episode, we're going to start with limits, because what else would we be covering? Now, the general formula template thingy is, I don't know the term, for limits is written as such. Basically, what it's implying is that x is approaching c. And as that happens, the value of f of x changes. Okay, yes. If this does sound familiar to you, it's because you could basically just think of this as functions from algebra. I mean, kind of. I say kind of because it is a little bit more complicated than that, but we don't know that yet. That comes a lot later. Now, there's a few representations of this that you're going to run into. Graphs, tables, and algebraic expressions. Yay, how fun. We're gonna start with graphs since you're likely most familiar with them already. Okay, please do forgive me for my horrible drawing, but let's just pretend that this is a graph. We have our x-axis and we have our y-axis, pretty standard stuff. And let's say I draw a curve like that. This is fx. And then I draw a point there, which basically becomes our value for c. Okay, I now realize that the way I'm speaking sounds pretty weird. Once again, the whole point of a limit is to describe the behavior of a function as it's approaching c. Now, that's all fun and well, but what if that's not the case? What if the associated y-axis at that point on the x-axis doesn't match up? Perhaps the y value jumps to something completely different from that moment. Say, for instance, -4. Let's write this out real quick. Now, what exactly do we do with the limit here? You might be inclined to say it's -4 since, well, the y value is now -4, but that's actually not the case. Now, in reality, even though the y value is equal to 4, it's actually still 2, because you are approaching 2 on the y-axis, assuming you're following f of x. So yeah, it's still 2. Now let's change things again, so it's just this one open point on the line. One now, because there's no more y value associated with that point on the x-axis. Well, honestly, it's not like it really matters. As it turns out, the limit is still 2 because we are still approaching 2 on the y-axis. So, yeah, that doesn't change. Okay, here's something new. What if I made a curve that loops back in on itself like this? Lopsided parabola, basically. I don't think that's the term, but And the first thing you might think is, what do we do now? Because there's multiple y values at that point. So is the limit 2 or -4? Well, as it turns out, the limit happens to be neither. There is no limit. It is undefined. I'm gonna make this thing smaller so it's easier to read. There. Undefined. There is no actual limit there because you can't really have a limit there. There is no real value for f of x. You can't come up with one because, well, remember, the rule of functions, every input can only have one output. If you don't remember that from your Algebra 1 class, can I ask what you're doing here? Anyways, moving on from that, now we are moving on to asymptotes. At this point, we have an asymptote at x equals -4. So, let's say the limit as x approaches -4. This is f of x, by the way. The limit of f of x as x approaches 4. Now, what exactly would the limit be here? Well, it just so happens to be undefined as well. It's actually outbound because at that point, you can't really come up with a value. That's the whole point of an asymptote. Another way you could think of it is the term out of bounds, kinda like in sports, I guess. Let's say, for instance, we have this person with a baseball bat. They do not have a name. I will leave that up to you guys. Hang on. And they managed to hit a baseball really far out, to the point where it's out of bounds. Now, let's say this is in a stadium, and it just goes completely over the stadium wall, which I don't think ever happened, but let's just say it did. Where exactly did it go? No one's really sure because it's behind the stadium wall and no one can really go back there. That's basically what's happening here. I don't really think that's the best analogy, but yeah. No, I don't play baseball, okay, or really any sports to begin with. So yeah, that's one way to think about this. Obviously, there's a lot more since it is just an analogy, but that's how I like to think about it, even if it might be pretty inaccurate. Anyways, let's move on to continuity, since that is technically still part of AP Calculus's first unit, so yeah. Let's say we have a straight line here. This is a continuous line. For the sake of mnemonics, we'll add a stick figure here, who sees it as a bridge. They can go that way, they'll be fine. They can go that way, they'll be fine. Now let's draw a curved line in this guy's back. This is still a continuous line. They can go that way, they'll be fine. They go this way, even though there's a drop, they'll be fine. But let's say we do something like this. This line is no longer continuous. Yes, they can go that way, they'll be fine, but if they try to go this way, what now? Because at that point, there is no y value at x equals 4. Ignore what I wrote, it doesn't make sense. So if they end up going there, yeah, they can't really do anything. Now what if we did this? Same thing, it is not continuous. Once again, they can go that way and they'll be fine, but if they go this way, it's gonna be a long drop, and we can't really afford to do that. Again, think of it as like a path or a bridge almost. We'll have these two stick figures. Hang on, let me draw the other guy in a layer so I can more easily give a visual demonstration. This guy, this is a continuous path, so he can walk back and forth. There are no gaps or anything of the like, so he can walk there, he can walk back there, just anywhere on the line as he pleases. But going back to the example where there was a open point, now there is a gap, and just for the sake of demonstration, this guy can't jump. So yeah, at that point, you can get really close to the gap, really close to it and still be fine, but as soon as he's actually there, he falls. Let's take things a step further and actually replicate that example I had earlier with the diverging paths, I guess. in any normal case, you'd have a ladder here, but we don't have that. So what do you do now? You can't really fall down there without breaking a few bones, which we can't really afford either. So you're kind of just stuck there. Sort of can't get down. That's kind of what's happening here. If I draw this again. You can't really get down without just taking a huge plunge, so at that point, not much you can do. Anyways, let's keep this from sounding too dark and we'll move on to tables, which is ultimately a lot easier. I'm pretty sure you know how tables already work. You put in an x as your input, f of x becomes your output, and then you just write down the associated values. Pretty standard stuff. Now let's say we have these really precise values like 5.99, 5.999, 5.9999, and the f of x value keeps getting more and more precise. And then we have something like 6.01, and the value is the f of x value, is 7.68. So what would just regular 6 be? Perhaps 7.66, 7.67? Good guess, but there's actually 3. At least in this context anyway. That's basically limits. The limit as x approaches 6 in this case, well, limit of f of x as x approaches 6 is not 3, but actually it's 7.6 something. Sorry, I completely messed up the visuals here, but this is basically what it would look like. I just completely messed it up. But yeah, basically what happens here is that there is an open point up there, so once you get there, you're not really there. You kind of just fall through like it's a hole. And then you wind up where the actual y value is. Anyways, with that out of the way, let's just hurry up and get this final part over with. Algebraic expressions. They're probably the most complex part of this whole thing. Now let's try to write something down. The limit of some expression as x approaches 5. Honestly speaking, it's just substitution all over again. Just algebra. You can tell how done I am with this through my voice. But yeah. Alright, this is where things get a little complicated. Now if you try to solve for this, you get 0 over 0, which is basically just 0 divided by 0. Now, this is not undefined. This is what we call indeterminate form. It means that there is a limit, but we do have to work for it. Now there's a few ways you can actually do this, but for time's sake, I'm just going to focus on factoring. I'm actually going to change the expression so it's easier to represent this. Hang on 1 second. Okay, this seems like a good one. So we'll just take what we have and factor it real quick. I don't think I need to explain factoring because you likely already learned this in your algebra classes, so in the case that you haven't, please do learn that first. Now, we don't like copies when we're factoring, so what we can do is cancel these two out, and we are left with x squared with x plus 5 parentheses over x. Oh, and also this is as x is approaching 2, I forgot to mention that. So the limit of x squared with x plus 5 in parentheses over x as x approaches 2. Yeah. But that's only if x isn't actually at 2. Because, well, we already know that that's going to be 0 over 0. Sorry if this is getting a little confusing. My brain is foggy. But anyways, in order to actually find the limit, we're going to be using a completely different function, g of x, and then input our factored function, because f of x is basically just the old function but rewritten. And remember, that gave us indeterminate form. G of x, on the other hand, is different. Its expression is completely different, so it doesn't hold the same restriction of it having a certain value only when x isn't a certain other value, I guess. So, as x approaches 2, the limit becomes 14, as you just saw me solve it earlier. And that's basically how that works. And honestly, I think we're pretty much done with limits. The remaining episodes and their associated topics will be released at a later date. When exactly, I honestly can't say for sure, but I know it will happen eventually. Also, yes, I know I have not been uploading recently. I have been busy, so yeah, I managed to get an actual job that's not just YouTube, so that's been taking up a lot of my time. And I'm also in theater, so yeah. Anyways, bye.